All right, let's get into the mole concept, and we'll start with balancing equations. First, you need to be able to take a sentence or a statement and be able to balance an equation with it with state symbols. So, a precipitate of lead 2 chloride. So let's try to make a formula for that. Well, we know that that's going to be lead chloride, lead 2 chloride, so lead 2 plus, chlorine minus, so that's going to be PbCl2, and then an aqueous potassium nitrate, well, KNO3. You should know your polyatomic ions now, and are formed when an aqueous solution of lead nitrate, lead 2 nitrate, so that's going to be PbNO3 with the 2 on the end, and then a potassium chloride, right? A lot of times that's just the hardest part. Now you go back and read through it again and make sure you identify every single word. So this is a precipitate of lead 2 chloride. So that means the precipitate is in the products section, right? So that is going to be lead chloride, and it's a precipitate, so it has to be a solid. Now you can put your state in the bottom left, or I put them below sometimes. It doesn't really matter. So precipitate and aqueous potassium nitrate, AQ, are formed when aqueous solution of lead nitrate, lead 2 nitrate, and potassium chloride are mixed, KCl, aqueous and aqueous. Now what this looks like, everybody, zoom back and try to understand what type of reaction it is. This is a double replacement reaction, or a precipitation reaction. Often that's kind of what you'll see. You'll see 2 aqueous solutions. You'll see 1 aqueous solution in the products and then 1 solid in the products. That's very, very common. So double check to make sure it's balanced too. So let's make sure that we put a 2 here to balance the chlorines. Now there's 2 potassiums, so there's 2 here. 2 nitrates, 1 lead, 1 lead. We're all balanced. We're good to go. All right. So that's how it goes. Make sure you identify every single word right here, and you are paying attention to everything. Now, when we make balance equations, quick thing is I try to identify what type of reaction there is. In IB chemistry, in pre-AP chemistry, we taught you 5 different types, but then in IB chemistry, we're going to really be focusing on only 3. So there's redox, which is, well, this is a combustion reaction because you have hydrocarbon with oxygen makes CO2 and water, just like this one. Now, those are always going to be redox because you are oxidizing this, right? We'll get it. And then this is a precipitation reaction because we are making a precipitate. Now, this one right here, I looked this one up. I kind of thought about this. This one was, I think this is a base, and I think this is an acid, and this is actually an acidic salt. So this would be an acid-base reaction. Now, why is it not a precipitation reaction? It looks just like that one. Well, it's because there's no precipitate here. All right. So this is a very kind of loosely acid-base. This is definitely redox because it's a single replacement right here, and this is a single replacement. So this is a good review on types of reactions as well. So let's see if we can balance them real quick. Welcome back. Hopefully I didn't make a mistake. Let me know in the comments if I did. So, all right. So moving on. Molar mass and the relative molar mass. All right. Key differences here, where molar mass they are the exact same number, but there's a difference. The molar mass is found on the periodic table, and the units are grams per mole. Relative molar mass is a dimensionless number and has no units. Okay, they will trip you up on that, and they love to do that one. So understand the difference between molar mass and relative molar mass. That is comparing it to the actual mole definition, 12 grams of carbon of carbon 12. So yeah, just keep that in mind. They're the same number, but same number. They really represent the same thing, but they're two different things. Let's try some mole conversions. Notice the graphic right here. It could be helpful when you're trying to convert moles to grams, the whole molar mass. For moles to liters, you're going to multiply by 22.7 if you're at STP. And then if you're going from moles to particles or atoms, molecules, whatever, ions, formula units, you're going to use Avogadro's number. IB likes to use this capital N and an A for number, A, Avogadro's number. So how many moles are in 19 grams of CO2? We'll just take 19 grams of CO2. Now, you remember, hopefully you remember dimensional analysis where we multiply by a fraction. We take this unit, we put it on the bottom, and grams to moles. And so the 1 goes with the mole, and G stands for go to the periodic table to find the molar mass of CO2, which is 44. And that's going to be 0.43 moles. And what's the mass of so-and-so atoms of zinc? 2.5096 times 10 to the 26 atoms. I'm going to convert atoms into moles by putting Avogadro's number and then moles into grams of zinc. Go to the periodic table for zinc. That's 65.4 grams per mole. And you should get an answer of 2.7263 times 10 to the 4th grams of zinc. You do need all those sig figs because you started with all those sig figs. So how many hydrogen atoms are in 39 grams of water? So 39 grams of H2O, grams to moles. The molar mass of water is 18. And then change moles of water into atoms of hydrogen. Well, you think how many atoms of hydrogen are there in oh, wait. Hold on. Yeah. Moles of H2O. I was one step ahead into a molecules of H2O. Sorry. So you are going to convert moles into molecules here because we need to know a huge number of molecules. So that's going to be Avogadro's number of molecules in 1 mole. And then think for every 1 molecule of H2O, how many atoms of hydrogen are there? There are 2 atoms of hydrogen in 1 molecule. So essentially, you're just doing this multiplied by 2. And so that is going to be 2.6 times 10 to the 24th atoms. And then it asks, what mass of NaCl would contain the same total number of ions as 245 grams of magnesium chloride? Magnesium chloride is MgCl2, because remember, Mg is in the second group, so it has a 2 plus charge. Cl has a 1 minus charge. So 245, this is the way I figured this out, is that I've figured out how many grams of magnesium chloride there are, and I want to know how many ions of magnesium chloride are in 245 grams. So I'm going to take grams and I'm going to switch grams to moles. And that's going to be 95.3 grams of magnesium chloride to moles. And then moles to molecules. We'll put Avogadro's number on top for molecules and the one next to the mole. And now for every molecule, there are 3 ions. For every one molecule, there are 3 ions because there's 1, 2, 3, right? Okay. Now that equals 4.642 times 10 to the 24th. Okay. So that is a lot of ions. Good. Now we'll go with that. Now we're going to say the same number of ions. Now we're going to see we're going to go backwards now. We're going to go from ions back down the chain, but except we're going to end up with grams of NaCl. So that should be MgCl2. Sorry. So we're going to start with 4.642 times 10 to the 24 ions, and then that will give us a total of 226 grams of NaCl. Rounded, of course. But rounded to 3 sig figs because we had 3 sig figs here. Now, does that make sense? Well, you had more here, but magnesium chloride weighs more. So that makes sense, right? Yeah, they all have the same, that many grams of NaCl has the same number of ions as that many grams of MgCl2. That makes sense because MgCl2 weighs more than that. All right. Now let's do some stoichiometry. Now, stoichiometry is when we're using a chemical reaction. We're combining that one thing into our chemical reactions. Now, notice the mole map right here. That is just a reference point for remember all the stuff that we did. So let's see if we have a reaction vessel is filled with 4.04 grams of hydrogen gas and 16 grams of oxygen gas, and the mixture is exploded to form water. Identify the limiting reagent and deduce the mass of water produced. Well, let's start with our chemical reaction. We had hydrogen gas with oxygen, and it exploded to form water. One of my favorites. All right, so, and then we had 4.04 grams of hydrogen, and then we had 16 grams of oxygen. Now, we have 4.04 grams of hydrogen. Now, this is a limiting reactant problem. I know I can tell because I have quantities of 2 different reactants. So we know we'll have to compute the limiting reactant first. So the trick here for computing limiting reactants is to figure out the number of moles first. So let's figure out the number of moles for each. Now we're using H2 here, molecular quantity. So that's going to be let's just do 2 grams. And so it's going to be 2.02. That's how many moles of hydrogen there are. Now let's find 16 grams of oxygen. Now grams of O2, moles of O2. Now O2's molar mass is 32. So you're going to end up with 0.5. Okay? Now, moles of O2. Now, an easy way to do this Now that we have the number of moles of each reactant, we're going to divide them by their coefficients. Divide this one by hydrogen's coefficient is 2, and divide this one by its coefficient, which is 1. Okay, so that's going to be 1.01, and then that's going to be 0.25. Now, whichever one is the lesser value is the limiting reactant. That's the easiest way for me to do limiting reactant problems on a time test. That's the fastest way. Just find the number of moles, divide by the coefficient. The least number is going to be the limiting reactant. Now you can do it the long way. You can actually compute. The limiting reactant is defined as the one that produces the least amount of reagent. So you can do the calculation basically right here, and then you can then convert them to one product, the moles of one product right here, using that mole ratio, which basically is dividing by the coefficient, right? And you will get to something like this, and it will be the lesser value. It just so happens that this will always be the same case as the one I just showed you. So this is just a shortcut. All right? So that's how you find the limiting reactant. Now the mass of the water produced, I just showed you, was going to be 1 mole. But if we have 0.5 moles of O2, let's convert moles of O2 to moles of H2O using that mole ratio. So the mole ratio is, we get them from the coefficients in the equation. The coefficient for oxygen is 1, coefficient for water is 2, so it's going to be 1. All right, and 1.00. That's the least number of sig figs. Moles of H2O. We should convert it to mass, of course, because they answer the question. All right, so we're going to multiply by 18, so we'll get 18.0 grams. Calculate the volume of carbon dioxide produced when 1 gram of calcium carbonate reacts with 20 centimeter cubed of 0.3 molar hydrochloric acid. And we're going to assume it's at STP. So let's go ahead and try to write an equation. We had calcium carbonate, and then it reacts with hydrochloric acid. So that is actually an acid-base reaction where we'll have calcium and calcium chloride, and then we'll have water, and then we'll have CO2. Then let's balance that. So let's go now. Let's figure out, we had 1 gram of this stuff, and we had 20 milliliters. Remember, centimeters cubed and milliliters are the same thing. And 0.3 molar HCl. All right, so we have 2 reactants. We know the quantities of both of them. So one of them is going to be a limiting reactant. We need to find the limiting reactant first. So that's going to be, let's follow that same procedure as before. 1 gram of calcium carbonate. And let's find how many moles that is. Grams to moles. And calcium carbonate's molar mass is 100. That's why we like to use it. So use some mental math. That's 0.01 moles. And then we'll take our, we'll find the moles of HCl just by taking 20 milliliters. And we'll convert milliliters into moles using that molarity, because molarity is moles over liters, right? So it's moles over liters, so we have to put 1,000 milliliters here, and that's going to be 0.3. And when we do that calculation, that's going to be 0.006 moles. So then I told you, remember what I told you? Divide it by its coefficient. The coefficient of calcium carbonate is 1. Coefficient of HCl is 2. So that's 0.003, and that's still 0.01. The lowest number is going to be your limiting reactant. So go ahead and write an LR underneath it. That can help. All right, so that is the one where we'll use our calculations with. We'll just say that we know that there were 0.006 moles of HCl that were used, right? We got that from this number. I'm kind of skipping this little step. And so now let's see how many moles of CO2 was produced. Okay, so we'll use that coefficient, that we'll use that mole ratio right there. So we'll do 2 to 1. And then we will convert moles of CO2 into liters of CO2. And that's going to be 22.7 and 1 mole. Because you remember that 1 mole at STP is 22.7 liters, right? So we can do that, and we can find out the amount of carbon dioxide produced. So that's 0.006 divided by 2 times 22.7, and that's going to be 0.0681 liters of CO2. That's 3 sig figs. We should round to 1 because there's 1 sig fig here. So let's round to 0.07 liters of CO2. Put that in a box so my grader can see that that's my final answer. All right, take a look at this next question and really pause and think about it and how you would answer that. Okay, welcome back. An acid tablet with a mass of 0.3 grams containing sodium bicarbonate, baking soda, was added to 25 milliliters of 0.125 molar hydrochloric acid. After the reaction was complete, the excess hydrochloric acid required 3.5 milliliters of 0.2 molar sodium hydroxide to react the equivalence point in a titration. Calculate the percentage of sodium bicarbonate in the tablet. So there's a couple of things going on here. We had sodium bicarbonate and we added it to acid, but we had acid left over, right? Then we can find out how much acid was left over from this stuff right here, from this titration. So what we are going to do is we're trying to find the moles of acid that it took to neutralize this tablet. The way we'll do that is we'll find the moles of acid at the beginning, and then we'll subtract it by the moles of acid at the end of the first reaction. Because there's really 2 reactions going on. There's a reaction with this tablet, and then there's the reaction with the titration. And then that will give us the moles NaHCO3, right? So the moles of acid at the beginning should actually be pretty easy to figure out, because all we have to do is just focus on this part right here. We'll just take 25 milliliters. And we'll convert milliliters into moles. And that's 0.125 milliliters to moles. That's 1,000 milliliters. And that's going to be 3.125 times 10 to the 1, 2, 3, 10 to the minus 3 moles. So that's 3.125 times 10 to the minus 3. Now the moles of acid at the end of the first reaction. Well, that it can be calculated from this part right here. Okay? So if we say that there were 3.50 milliliters of NaOH, milliliters to moles, 1,000 milliliters, 0.2 moles of NaOH. And then we can do that moles of NaOH to moles of HCl. And that's a 1-to-1 ratio, right? Because you know that HCl plus NaOH, you know, that old classic acid-base titration, that's a 1-to-1 ratio. Just hopefully remember that. Trust me on that. And that will be the moles of HCl. So that will give us 7 times 10 to the minus 4 moles. Conveniently less than the first one, right? 7 times 10 to the minus 4. Okay, so this number minus this number is going to give us this number, right? The moles of acid used to neutralize it. That is going to be 2.425. I'll save you the calculation. Times 10 to the minus 3 moles of acid to neutralize. NaHCO3. Okay, so I'm just going to try to separate things here because we're running out of space. Now we know that the sodium bicarbonate plus that HCl made an acid-base reaction to make NaCl plus H2O plus CO2, right? So I just wrote that out to make sure that this is all a 1-to-1 ratio. The coefficients are all going to be 1. This is a balanced equation. No like flip-flop is going to go on. But what we are going to find out is that the moles of the acid required to neutralize this, we can use that to figure out the moles of NaOH there was. And then we can convert the moles of NaHCO3 into the grams of NaHCO3. So stick with me. That means that this actually means that since we took this many moles of acid of this, that means that that is the same number of moles of, here, I'll write that out. Moles of HCl to moles of NaHCO3. That's a 1-to-1 ratio. And then we'll convert moles of NaHCO3 to grams of NaHCO3. And the molar mass is going to be 84 grams. So when we figure all that out, that's going to be 0.2037 grams. That is of NaHCO3 was actually present, which means that the tablet was 0.3 grams. We're trying to find the percentage right here. So I'll go ahead and write on the bottom. What we'll do is we'll just take we'll take the part over the whole, 0.2037 grams, and we'll divide it by the whole, and multiply by 100. And then that will give us 67.9%. And that is fantastic because that's exactly what we want. And that is 3 sig figs. That's the least number of sig figs in the problem. And we're all good to go. Thanks.